Yay. Okay, thanks everyone. Yeah, it's really fun to be here, first of all. I remember, I think I actually met Koen once before the next speaker. Maybe he doesn't remember it, probably not. But many years ago, just after iOS 2 came out, I went to the CocoaHeads meetup at the SOFA offices here in Amsterdam. This is a long time ago. And it was really funny because there were all these Mac developers who've been doing that for years. And then there were people like us, the young, new iOS newbies, and we had basically no clue. We were writing things like retain and auto-release, and we didn't really know what we were doing, but it was fun. So it's cool to be back. So this is my terminal. I don't have any slides prepared. I know it's a bit weird because I make an app called Blackset, which is made an app to make presentations and to make slides, but I didn't have any slides. So we're going to do live coding, which is always a bit scary, but I practice, so we'll see. I might make a mistake, and then please help me out. So let's just start a new project. I didn't prepare anything, so we're going to create a command line tool, and we're going to do some sorting today. So let's see. If we run this, hopefully we'll get a hello world. I need to increase the font size of the console. One sec. And you can see that as well. Cool. Can you see the hello world? Is the banner not blocking it?
Yeah, the banner is.
The banner is blocking it.
The banner is blocking it. Should we remove it? So please have a good look at the banner. Not to make it block it away. This is putting extra focus on the banner. Beautiful banners. Cool, now you can see the hello world, right? Awesome. So, what we're going to do today is use quicksort, and we're going to use the quicksort that's built into the system that's in the C standard library. So we're going to look at how Swift and C interoperate. And maybe a first question is, why would you ever want to do this? Why would you want to work with C? Well, I think now that we had the announcement that Swift is open source, this might become very important, because what happens when Swift is available on Linux? We can all of a sudden write Swift, but it's very unclear which frameworks will be available. I don't know, I guess Apple will not port everything to Linux and make all their frameworks available. So we'll have all these problems we want to solve, but we will not have libraries. And that's why it's super important to know how you could work with C if you want to wrap some C libraries yourself. So, you know, like things like core graphics will probably not be available, and we might need to wrap them ourselves. Or wrap something else like Cairo or some other rendering engine. So that's what we're going to do. And we're going to take a look at a very simple example, namely quicksort, which you should never have to wrap, but it's a nice example to illustrate how to do this. So let's create an array. So I'll just put some random stuff in the array, and 5 maybe, and call this numbers. So what we now can do is we can print the numbers, and we get the numbers out, and we can also sort the numbers, and let's see, there are the numbers. We can sort the numbers, and then we get a print of the sorted numbers. So far so good. This is what you always should use. Just use the built-in Swift sorting. Never use any kind of quicksort wrapper. And what is cool about this is the sorting returns a new array. So if we now print the numbers again, you'll see that the original array did not change. Hopefully. Yeah, so first we get the sorted numbers, and then we get the original array. What is also cool, you can do something like this in Swift. Sort in place. However, we get an error. So the sort in place sorts the number array and changes it. So now the numbers will be different. We define numbers using let, and this means that it's a constant, that it cannot change. What we need to do is click on this error and let Xcode help us I'll zoom in a little bit. So it proposes to change this let to var. If I press enter, it changed let to var. And now we can sort the numbers. So Xcode will help you with this. So if you want to sort an array in place, then this is the way to do it, and you need to define the array using var. So now you can see that the array is sorted if we print it. So that's really cool, this kind of behavior. Okay, let's try to do quicksort, because this was easy. I'm going to make it slightly more complicated with every step. We'll start with something simple. So we'll just type qsort, and then we get this thing. Unset mutable pointer void, int, unset pointer void, arrow, int 32, and an exclamation mark. What does this mean, and what do you put in here? So I'll show an old trick. That's why the terminal is open. You can type man qsort, and then you go to the manual page of quicksort. And here there's descriptions. So if we scroll down a little bit, there's 3 versions of qsort. And let's look at the first one. So it says void qsort. This void is the return type. It means that qsort is not going to return anything. It's going to return void. So that's already a sort of a hint, you know. Quicksort is not going to give us a new array. It's going to change the existing array. Then there's void star base. So this means the void pointer to base, to the first element in the array we're going to sort. So it's a pointer to the first element of the array. And this is how arrays work in C. And then there's the number of elements. So this is the number of elements in the array. And then there's a width. And this is the size of a single element in memory. And using these 3 parameters, quicksort can sort of iterate over the array, and it knows how wide each element is, and it knows how many elements there are. So it just starts with the first, with a pointer to the first element, and then it increments that. And then the final thing is a C function pointer. So this function pointer is called compare, without the E, and it returns an int. That's on the left side of the compare, so I'll select that. This is the result of the function pointer. And then it takes 2 parameters, which are const void star. So before we saw the void star to base, to the first element of array, and this void star sort of is a C kind of way to say this can be anything. So this is a pointer to anything, we don't really know. And it's the same here in this comparison function. It gets called with the 2 elements to compare, the left element and the right, and because we don't know the type, it's void star. And then there's this const modifier, which says that you cannot modify the elements. So basically, the first pointer to the base is an array that we're going to mutate. In the comparison function, we get the 2 elements, and we can compare them, but we cannot modify them. That's why it's const. Cool, let's try to use this. So back to the code. So we need an unsafe mutable pointer of void. In Swift, it's actually really easy to create this. You have to know it. You can just type ampersand numbers. That was very easy.
Wow.
Yes. And then we need the number of elements. So we can just say numbers that count. Then we need the size of the single element. And I'm going to make a mistake here. So I'm just going to do it like I would have done in C. Size of int. Later on, if we have time, we can see why this is a mistake. And then we need a function pointer. So if we tap and press enter, Swift generates a closure for us. So we can use closures in Swift as C function pointers, so we can make it very easy to work with them. Inside these closures, however, we cannot refer to any variable outside or anything outside of closure. And we'll see why this is a problem later on. So we get 2 unsafe pointers of void. Let's see. Where is my cursor? Yes. So we get a left element, and we get a right element, which are both unsafe pointers to void. And then we need to return something. So let's just return 0 for now, which is an int 32, and run this. We're not actually comparing, so the array will not be sorted. And then we need to print the numbers, of course. So now, at least the program didn't crash. We successfully called the C function, but it doesn't really do much. So we need to compare these 2 integers inside this callback. And the first thing we need to do is to cast these void pointers to integer pointers. This is how you do it in C. You need to cast pointers, and this is an unsafe operation. So what we want to do is something like left is an unsafe pointer to an integer. And to cast it, we can just say unsafe pointer left. And this will automatically convert it to the right type. And the same for right, the other element, unsafe pointer in. And we can do the same conversion. And then we can compare the memory of these pointers. So if you're used to C, in C you can dereference a pointer. In Swift you can just look at the memory of a pointer. So what we can do is something like this. If left of memory is smaller than right of memory, and in auto completion you see that memory is an integer. So if left is smaller than right, we return -1. If they're equal, we're going to return 0. Return 0, and otherwise we just return 1. And this is how, if we would have kept on reading the documentation, how this callback should behave. So it should return either -1, 0, or 1. So let's try to run this. And we have a sorted array, 1, 3, 5, 7, 17. So we finally successfully called quicksort. This is cool. It's very complicated, right? And this is the easy version. Okay, so what I want to do is I want to also make this work on arrays of strings. And before we can do that, I'll just put this inside a function so that we can keep calling it. So now, of course, we're sorting the numbers in line. So let's create a function out of this. I'll call it quicksort. And I'll just put everything inside the function and indent it a little bit. So let's think about the input and the output. So the input has to be an array. Input has to be an array of integers, and the output is also going to be an array of integers. And now instead of using numbers, we should of course use input, and then return input. And now we get the same problem again. We get this error message here saying that input is a let, and make it var. So if we make it a var, the Swift compiler is happy. So let's think a little bit about what happens here. So if you call a function with an array, in Swift this works the same way as creating a new variable. So instead of putting a reference to the array, the function gets a copy of the array. It's not actually a copy until you start modifying it, but you have a new array to work with, so the original array doesn't change. And by writing var here, we're still not changing the original array, but at least we have something we can mutate. So now we have a copy of the input inside a variable, and that's something we can change in quicksort. So let's try to call this function so we can print numbers twice, and then the first time we'll quicksort it. Numbers. Okay. So here you can see that behavior. First, it sorted the numbers and printed it, but it did not change the original array. So the moment you call quicksort with an array of numbers, it makes a copy, and then we can change that copy. So this is cool. Now we have quicksort for integers. Let's do it for strings as well. Okay, I'm just gonna first copy paste this. This is how I like to do programming. I think Ilko once coined the term Oreo, only repeat yourself once, rather than don't repeat yourself. So let's make this work on strings. And I'll just try to call this on an array of strings. Hello, and world's lowercase, and hello uppercase. And hopefully we'll have some kind of problem. So let's see what happens. Boom. So anytime you work with C code, this can happen. This is a very simple example. Probably if you're writing a library, you'll have more complicated code, and stuff like this will happen. So let's think a bit about what actually happened. We changed the type of quicksort to accept strings and return strings. And then here we set size of int. So we're comparing, the quicksort loops over the array, but it increments only by the size of an integer in memory. And we should have said string. And if you're wrapping a C API, it's almost certainly going to be unsafe in this kind of way. Like, you don't really know what the types are. Quicksort, for example, works with these void pointers, and it's all very much untyped. So this is something to be very aware of when you're wrapping C. You need to be very careful about memory and about passing in the right types, because if you don't pass in the right type and if you make mistakes, probably your code will compile fine, but it will crash at runtime. So let's fix this. If we change this to string, now we will get an array printed, but it's not sorted in any kind of obvious way. And this is because in our callback function, we're still comparing integers. So over here, we need to change this to string as well. So let's do that. And run it. And now finally we have a sorted array of strings. So first all the capital words, and then the lowercase words. And hello comes before world. Okay, so this is a lot of work. If we want to keep adding more types, we have to copy and paste. And that's of course painful, so let's use generics. I know how to do this, I think. Let's see. So what we want to do in Swift with generics, we can say, well, we can sort for any A, we can sort an array of A's and produce an array of A. And this is already, Xcode went black. All the syntax highlighting is gone, yeah. So we change this string to A, and we can also change this to A, and this to A, and try to run it. Build failed. So there's two problems. The first one is easy. So here it says binary operator cannot be applied to two A operands, because what this type says, like, this really works on any kind of A you want. And what we really want to say in our function is we only want to sort the things that we can compare. So here you can say, for example, A needs to be comparable. And now we sort an array of comparable things. And this is, of course, something that will work. So build failed. Now there's no error message, nowhere in the file. And we can go here and look at the segmentation fault. So let's see. There's a stack trace, and this is becoming less and less common with Swift, but it might still happen that you run into a compiler bug. So what to do?
How can size of work?
How can size of work?
On string and on an int?
It's a good question. In this case, it will work. The memory for a string is constant because inside the string is a pointer to the character. So
okay.
Yeah, in this case, it will work. Size of is almost fine. Size of is not a problem. So the problem is that inside this closure, let's see, we're referring to an A. And if you recall, like in the beginning, we talked about how a C function pointer you can put closures in there, but they cannot refer to anything outside of the closure. And this is the problem. We're referring to this A, which is basically something from outside, and that will not work with C function pointers. So what we can do is take this closure. We could, for example, try to put it into a separate function. And then the problem becomes a little bit more clear. So this function looks something like this, right? Like it takes, so it's a compare function, and for any A that's comparable, this is a callback. It would take an unsafe pointer of integer, and another unsafe pointer of integer.
Unsafe pointer of A.
A, yes, thank you. This is so easy to make a mistake. Actually, the thing is, it takes an unsafe pointer of void. That's what quicksort wants. So it's even more complicated. And it returns an int32. And here you can already see that this A is never used inside the type signature. And Swift also doesn't really allow us to write this in this kind of way because it doesn't know how to fill in the A. And so I tried this approach and it doesn't work, unfortunately. Okay, so the thing is, with this quicksort with this quicksort function, there is no way to make this work, unfortunately. And it's a hard limitation of the way how C works. We want to pass in some kind of context, the A, or at least how to compare A's. And the C API doesn't allow us to do this. And C programmers have this problem as well. They could not write something like this either. So let's go back to the manual and use a different quicksort. So here we had 3 versions. Let's look at the second one. So the second one says void quicksort B, so it's quicksort B. It has a void pointer to base, the number of elements, the width, and it also has a comparison function pointer. However, this function pointer is not really a function pointer, it's a block. If you look very closely, you can see that this one has a caret and the other one has a star. Like it's this caret. So it's a block. And blocks are really cool because, as you know from Objective-C, they can refer to things outside. So let's just try to use quicksort B instead and run it. And it compiles, it runs, and it sorts. I can remove the integer version. And so we were able to sort strings. We can also maybe sort some numbers. Quicksort 1, 3, 2. And this also works. Basically, we're done. So if there is a block-based version in the C API that you're calling, just use that and you're done, and you can use it from Swift and everything is good. So I could end my presentation here. However, I want to make it more complicated. It's okay if you lose all the different parts after this. It's fine. Now we're going to make it more complicated because most C APIs that you work with will not provide you with a block-based API. So it's very, very uncommon that you actually have a C API that takes blocks, because blocks are this Apple thing, or at least Apple added them, and they're highly uncommon. So what you will see often is something like the third variant of quicksort in the manual page. So let's take a look at that. It's also void, returning void, so it also starts in place. It takes a base, a pointer to the first element, the base argument. It takes the number of elements, it takes the width, and then it takes an extra argument, the thunk. And inside this comparison function, we can now also see that it takes 3 arguments rather than 2. So before the 2 elements, there's this extra void pointer. And this thunk is sort of like context we can give to the quicksort function. It's something we can put, because it's a void pointer, we can put anything we want in there, and in the callback, we get it back. So if you're, in a way, it's sort of like in NS notification, you have this thing that you can set, which you can pass into a notification. You can basically put anything in there in the user info of a notification, and you just get it back unchanged. The user info in an NS notification is untyped. You can just put anything in there, and when you get the notification, you also are not really sure what was put in there. And so this is basically the same idea. In this quicksort function, we can put anything we want inside this thunk, and we get it back inside our comparison function. So what we're going to do is we're going to use this, and inside our comparison, what we're going to put in there is a function to compare 2 void pointers for a specific A. And then inside our callback, we're going to get that function out again and call it. So this is complicated. The thing is, many C APIs work in this kind of way. So once you know this technique, it might look very arcane now, but once you know this technique, you can wrap many C APIs because almost all of them use this technique. Let's do this. It's going to get complicated. Okay, so I'll comment this part out for now. Actually, we'll just delete it. This is scary. Okay, so quicksort R. It wants the array, so input, and a pointer to the array. We want input.count. We want size of A. And then we need to, we can put in any kind of context. And what I want to put in there is basically a function to compare two A's. So before we can do that, I'll write this function first. So what we can do is something like this. We can extend comparable, and this basically says, this adds a function to every comparable type. And we're going to write a static function, and this is going to have the same type as the original comparison block that we had. So this function is called compare. And on the left-hand side, it takes an unsafe pointer of void, and it takes another unsafe pointer of void, and it's going to return an int 32. So this is basically the same function that we wrote before. I'll just write it in a little bit of a different way. So left is self, and there we can say unsafe pointer left.memory. Right. It's the same kind of trick. We get the memory out. So now, for example, if we call this on string, we have two strings. Oh, yes, thank you. We get two strings out. If we would call this an integers, we get integers out. So now we can say if left smaller than right, we return -1. If they're equal, we return 0. And otherwise, we return 1. Okay, so now we have this comparison function available. Hopefully the compiler is happy.
You didn't define the R yet.
I didn't define the R yet. Oh yeah, I need to write R. Okay, cool. What I want to do is pass this comparison function in there, because if you remember, I said we can just put anything in there. We could put an integer as our thumb, we could put an object, and why not a function? So let's just try to do that. A of compare, because it wants a pointer. And then what we can do inside our callback, so inside our callback we can use this comparison function. And to make it even more complicated, we're not going to write a callback. I'm going to delete this. And we're going to just write this as a top level function. And I'm going to paste it back in and clean up the syntax. So now we need to add names for the arguments. So this is our callback function, our thunk. Then we get the left element, and we get the right element. Okay. So we get this callback function from quicksort. We have this thunk. In the type it says unsafe immutable pointer void, but we really know that it is a comparison function because that's what we put in there. So I'll just copy this type, put it here, and say compare is going to be a function. And the way we can use this is we can again cast the unsafe pointer of thunk and say .memory. This is the same technique as we used before, and now we can call compare. So with the left pointer and with the right pointer. So this is complicated. There is one more thing we need to fix. So if I go back to documentation, you can see that this thunk is void star, and also inside the comparison function it's void star. And because it's just void star and not const void star, it's an unsafe mutable pointer. So it's not an unsafe pointer, it's an unsafe mutable pointer. And that means that this thing, the &a compare, needs to be mutable. And of course, the comparison function is just statically defined on this type, so it's not really mutable. What we can do instead is just create a variable and put it in there. So compare equals a of compare, and then we just pass the variable in there. Compare. So now this, because it's a variable, it can be used as a mutable pointer. Okay, so we're calling quicksort. We have all this magic going on with the pointers, and now we can just return the modified input. Let's see if this works. The old quicksort is gone, right? I deleted it. Yeah. Let's run this, fingers crossed. And it started. So this is how you can do that. It's very arcane, but this technique works for any kind of C API that has this void pointer thing going on. Sometimes it's also, instead of thunk, it's called context or something else. But with any kind of C API where you have void pointers, you can use this technique. Just put anything in the void pointer and cast it out later again. Okay, so just to close it off, I want to make it a little bit more Swifty. So this is, again, hopefully fairly easy and not complicated pointer stuff. So what we're doing now is we're calling quicksort with a function, with an array. And as we've seen in the beginning we did array.sort. So that would be nice to have that kind of syntax, just to be able to say array.quicksort. So we can just write an extension on array and put the quicksort in there. So I'll delete this one and put it in here. So now, because we're calling it on an array, we don't need this extra parameter anymore. So I'll just delete that. And instead of returning A, we need to return element, because that's the generic parameter of the array. We can delete this generic thing, and now we need to call it on self and self.count. This, of course, is not going to work. It's this thing with mutating again, that self is basically defined as a let, at least for now. So we need to create a copy of self. So we just call it copy. And var copy. Thank you. This is hard to like coding, but fun. So we sort copy, we say copy.count, and then we return the sort of copy. Almost ready. The size of A, of course, needs to be self, and this A.compare needs to be self.compare. However, what is the self.compare? How does this work? We need to make sure that we can only sort arrays that are comparable. So what we can do is say where element is comparable. And now we can only sort comparable arrays.
Shouldn't it be size of element?
Yeah.
Size of element, thank you. And it needs to be element of compare, of course. I knew there was something wrong, I just couldn't see it. So let's run this. Now we have to use the new syntax. So now we can say .quicksort, and we get a new array out, hopefully. Build failed. And there's another one, thank you. You're so helpful. .quicksort. So we can now call it, run it, and it works. And as the last thing, I want to recreate this sort in place, and also write a quicksort in place, and then we're done. So that would look something like this. Quicksort in place. And it's just a function that you can call, and then it modifies the existing array. So we can try to copy and paste this, and actually use self, and use self.count, and then we don't need to return anything. But the thing is, we cannot modify self. And this is something that's really cool in Swift. What you can say is mutating. And Swift will help you that you cannot accidentally write code like I was doing. You're forced to write mutating if you want to change this array. So only by writing mutating, self is actually a variable. And now we can say, for example, put this into a variable called numbers, or var numbers equals an array. It's going well with the copy and pasting. And we can say numbers.quicksort in place and call numbers, print numbers. And hopefully this will have sorted the array in place. Invalid redeclaration.
There's another numbers.
There's another numbers at the top. Did I define it as a variable? Yes. So now it sorted the numbers in place. Just to be sure, yeah, we didn't sort it before yet. And what you can even do is remove this part and say copy quicksort in place to share all the code. So we started with very simple wrapping, something non-generic. This works great. If you want to wrap C stuff in a non-generic way, it's almost always relatively easy. Then we made a generic, and we used the block-based API. This was also still simple. And once we started using the void pointers, it became complicated. But again, like I said before, this technique will work for any kind of C API. And the really cool thing is that once you have this quicksort function, you can make it really nice and integrated into Swift, like we did here with the extensions. So it's a lot of work up front. And however, if you do manage to finish the work of wrapping, then you can have it in a very beautiful way in Swift. I'll just tell you about this error, because otherwise I'll be spending 10 more minutes writing up an example that will crash this. So size up will mostly work. If you're used to C, this is how you would write in C. Most of the time it just works fine. However, what you really should write here is stride off. So let's run it. It will still build. Why stride off? So stride off also accounts for the extra padding in memory for a specific architecture. On some architectures you might have extra padding for your struct. And stride off accounts for this. And stride off is the function that you should be using. This was very, very unclear to me, and I was also very uncertain why my code would crash with size off. And this is basically what the Swift compiler people said, like you have to use stride off rather than size off, and then everything will work magically. And this is poorly documented, you just have to know it. So, it works like with a struct like this, where you have optionals, for example. If you have an optional name and an optional age, then you can make it crash with stride off.
Size off.
With size off and not with stride off. Thank you.
But
Okay.
This works. The struct is always just a piece of memory.
Yes.
Okay.
This works with stride off. Yeah. It works really well. Yeah. So
a string is not a C kind of string with a pointer. It's
no.
The memory of the string, and size of works on that.
Yes. So the size and memory of a string is constant. However, so it's a constant struct basically, and inside there's a pointer. But this pointer is managed for you. You don't have to know about this. There's no passing by reference and stuff like that. So it works just like any struct. So with that, I want to conclude, and I'm very happy to take more questions. Thanks.